written main. That is actually the master book that explains most of the history, how it has gone through, and where we are. So let's open it. I think I had it somewhere. Yeah, this one here. And it's quite so, but of course, when you are reading and you are revising, you can read it. But let me start by introducing by saying that before you do any text analytics, you need to be able to convert the text into some vectors or into some numbers, like a vector. Of course, if you can have some numbers like integers, like fractions, probabilities, and so on. But also you can have it as a vector. Now, the origin of it as a vector, we will just go straight there. So it says here, the role of context is important. Variety of a less biological kind of organism. Maybe I've skipped some things there. But what they are trying to say here is that you must understand the context of a word so that you can know its meaning. Like there's a simple example here, 19.1, that a bottle of whatever this is, this is just a nonsensical word. There's nothing like this, Tesguino. So a bottle of Tesguino is on the table. Everyone likes Tesguino. Tesguino makes you drunk. We make Tesguino out of corn. Corn is maize. So if somebody else was talking of that thing that you brew in Western Kenya, what do you call it? Busa, isn't it? So the busa could be maybe something is in a pot. So it might not have been a bottle, but it's in a pot. Everybody, or every gentleman in Luyaland likes busa. Busa makes you drunk. And maybe we make busa out of corn or out of maize. You see now, the context, they are more or less the same. So busa makes you drunk, Tesguino makes you drunk. So what probably are you talking about? We are talking about another beer somewhere. And therefore, you can tell that clearly these two things, Tesguino and busa, are very close to each other because of the context. And due to this, we use the context as the basis for our vectors. So I hope that is clear. So we use the context. That is the word surrounding the main word. We use it to generate the meaning of a word. So just understand that we're using the context. Now, how do you use the context? There are many methods that have been proposed. And one of the most critical methods, and this one, the guys in mathematics love it. This is the distributional methods. So in distribution methods in which the meaning of the word is computed from distribution of words around it. So these words are generally represented as a vector of numbers related in some way to counts. And so these methods are often called vector semantics. So the words surrounding it are represented in a vector form. That's why we call it vector semantics. Semantics, it means meaning. So it's meaning out being based on these semantics. So here, say we'll introduce three popular vectors. And they begin with what we call sparse vectors. These are usually high dimensional vectors. High dimensional vectors. They're also called long vectors. Long vectors. And they have very many zeros. You'll see where the zeros are coming from. But later on, we will. So there are these two popular methods. So there's the low density vectors, or the so-called sparse vectors. They're also called the low density or the high dimensional and so on. But on the other extreme end, we have these what we call the dense vectors. The dense vectors. That's on the other side now. And what happens is that these dense vectors, we will try to shorten the size of the dimension of the vector. It could be like 1,000,000 by 1,000,000. That's a very huge vector. Or 500,000 by 500,000. It's a very huge vector. And you will try to reduce it to something like a 50 by 50 or 100 by 100. So that is a more dense vector. And that dense vector, we call it an embedding. We call it an embedding. So we can have either sparse vectors or the embeddings, which are the dense vectors. And to move us from the less density to the high density, we have two main approaches that are discussed in this book. And this is the so-called the SVD, which is a dimensionality reduction. We are trying to reduce the dimensions from, let's say, 1,000 by 1,000 to say something like 50 by 50. So SVD is a mathematical formula or mathematical approach which can be used to reduce our dimensions. The other one is to use neural networks. To use neural networks, and the two popular algorithms. Now, these specific algorithms for these, there's one called skipgram and another one called SIBO. So these are neural network-based methods to do dimensionality reduction. And these are the two most popular ones, the skipgram and the SIBO. Now, somebody wants to join our class. I don't know who's that. Let's just allow the guy in. Let's admit whoever it is. It's a guy called Derek. He wants to join. Okay. So Derek has interrupted the flow of knowledge here. Yes, but we were saying, of course, to reduce to increase the density of our vectors, we have moved from low density to high density using either SVD or using neural networks, and that is either using the skipgram algorithm or the SIBO algorithm. And the most popular one, of course, you'll see is the second one, which is the neural network based. Now, we will start by distributional methods, which is, of course, now the long vectors or the low density vectors. One of the most commonly used methods, I say there are several methods, but one of the most commonly used methods is called the co-occurrence matrix. Co-occurrence matrix. Now, what is co-occurrence? Co-occurrence means that things have occurred together. Co-occurrence, occurring together. And one popular co-occurrence matrix that we can create is the so-called the term to document matrix. Term to document matrix. So what that means is that, of course, we can have a word to document, but sometimes we prefer to use a term. A term could even be a phrase. You know, like I can say wine, or I can have a phrase like a glass of wine, or I can have a bottle of wine. So all those things map onto wine. So what we do in this term document matrix, so on one side, you have the documents themselves. So here you can see the titles of the documents. There's a book here called As You Like It. It could be a document. A document could be either a book, it could be a chapter of that book, it could be just a short text like a tweet. Still a document. A tweet is a document. Or it could be a blog. So, this, assume this is a book. So this is a book called As You Like It, the another called 12th Night, Julius Caesar and Henry V. But here we have now the terms that are written in those books, like the battle, soldier, full crown. So how many times was it written? So here's just an account. As You Like It occurred only once in that book. No, the word battle occurred only once in the book As You Like It. All right? But the word battle occurred 8 times in Julius Caesar and 15 times in Henry V. Now, in the word soldier occurred twice in As You Like It, 2 times in the 12th Night, 12 times in Julius Caesar, and that 6 times in Henry V. The word fool, that 7 times, so that was a lot of times. And the word fool again occurred 58 times, but only once in Julius Caesar and 5 times in Henry V. Clone occurred 5 times in As You Like It, but 12th Night, it occurred 117 times, and the word clone never occurred in Julius Caesar and Henry V. So if I take the inside here, without now the titles, I can put square brackets that you're familiar with, and I can call that one a matrix. So the matrix would be on the no, I've forgotten the M and the X. The M and the N column. The rows, the rows will be 1, 2, 3, 4, 4 rows. That is the battle, soldier, fool, and clone. And 1, 2, 3, 4, 5 times. 1, 2, 3, 4. 4 times on the column side. That's depending on the title of the books. So that's a 4x4 matrix. But then you can ask yourself, how many words would you like to model within these books? They're in terms of maybe hundreds of thousands. So this will be a very large vector with so many zeros, because some of the words will not be occurring in those books. So that is a very simple way of representing a vector using the term and the document. So I'll skip a little bit of this. This is just explaining what I've just explained. And now from this one, can you be able to appreciate which books are talking about war and things like, where fighting is occurring? Because wherever there's battle and soldier, there could be fighting. So Julius Caesar and Henry V clearly are books whereby there's a lot of fighting. But Fool, probably this one is just talking about fiction stuff. So As You Like It and 12th Night are fictional books, and so on and so on. So from our matrix, you can be able to discern a few things, like these books are fictional, these ones are clustered as maybe referring to war and competition. All right, so here they're just explaining the way you can also plot these ones on a graph. For example, the book As You Like It. As You Like It, this is plotted as what? As You Like It, 1, 2, that's, I think they have only used 3 dimensions. They have removed the word clone. So they have 1, 2, and 37. So you plotted it is here. 12th Night, they have plotted 1, 2, 58. This should be 58, not 56. And then Julius Caesar, they plotted 1, 8, is it? Julius Caesar. No, Julius Caesar. Then Henry V is 5. I think they've gotten some numbers here wrong. But anyway, the idea is that you can plot these things on a graph and you can see which directions they are heading to. So here they're saying we can think of we can think of document vectors as points in a v-dimensional space. Thus, the documents in figure 19.2 are points in 4-dimensional space. Since 4-dimensional spaces are hard to draw in textbooks. Oh, that was the reason. Figure 19.3 shows visualization in 2 dimensions. And we arbitrarily show, oh, these are 2 dimensions. What was I reading? We've arbitrarily chosen 2 corresponding to the words battle and full. Oh, okay. So they did not do for all the 4 dimensions. They did it for only 2. So as you like it, it's 137. Oh yeah, 1 and that 7. So they've skipped the 2. And so on. So you can plot like that. And you can see generally, as you like it and 12, they are more or less converging towards one cluster. Julius Caesar and Henry V is clustering towards one place. So the whole idea is that you can use these vectors to do clustering. So you can see things are converging towards some clusters. So the term document matrix, they are originally defined as a means of finding similar documents. So I'm reading here. Similar documents for the task of document retrieval. So 2 documents that are similar will tend to have similar words. And if 2 documents have similar words, their column vectors will tend to be similar. All right? They've given the example of Julius Caesar and Henry V. I think information retrieval, as you know it, like now there we are just to see which books are alike, and so on. So so information retrieval is the task of finding document D. So you're looking for document D from the collection of documents D, capital D, that is, all right, in some collection that best matches a query Q. So like I take you to the main library, I tell you, look for books that are discussing computer science. So even without the word title computer science, which words will you look for? Probably you look for things like what? No, information might be too general. Maybe data, maybe machine learning, and all that. So those would be describing maybe similar terms that are normally used in computer science. So you can get all those books. Now, the first one we were dealing with here was what? Sorry. Term to document matrix. Now, this one here is just using this second one here. Where is it? I think I've just lost the trace. Sorry, let me look for it again. Yeah, so the next one is, of course, using words as vectors. Words as vectors. So the word vector is now row vector rather than as a column vector, and hence the dimensions of the vectors are different. So you're just reversing the columns here. Yeah. Now, you can also do another one called the term-to-term matrix. Term-to-term. Meaning that instead of, let me see if there's a better explanation here. Yeah, like this is a good example. This is term-to-term. And so what you do is that you now count. You now do what we call co-occurrence. So how many times do things occur together? Like here I have the words apricot, pineapple, digital, then information. And then on the column side, I have so many words, like adverb and so on, computer, data, pinch, result, sugar, and so on and so on. So you want to see how many words are occurring together. For example, the word apricot, which is supposed to be a fruit, if you know it, occurred 0 times with the adverb, 0 times with the computer, 0 times with the data, but 1 time with pinch. The word pineapple, it could be occurring within a certain window, by the way, for those who are wondering. Within a predefined window. Maybe you can say that window is 3 times to the left, 3 times to the right. So you strip all the full stops and everything. You just say, I just want to open it 3 times. I mean, three words to the left, 3 words to the left. So in total, you'll be having 7 words, and you're trying to see whether these words are occurring within that window. So if you take the word digital, for example, digital, it occurred 0 times with the adverb, but 2 times with the word computer. 1 time with the data, the digital data, and 1 time with the results. But information is also occurring once with the computer, 6 times with the data, and 4 times with the results. So you can see clearly terms that are not related at all will be very far, like apricot and data, or pineapple and computer. Those are very far. So you can see clearly they are far. And you can see down there, there's a plot. There's a plot here. So concurrence vectors for 4 words computed from brown corpus. So the vector for the words digital is outlined in red. Note that a real vector would have vastly more dimensions and thus be much sparse. In other words, what they're saying is that it will be sparse. It will be having so many zeros, because the word digital will occur 0 times with the elephant, 0 times with, whatever it is, with the ugali and so on. But with related terms, it will be there. So you can plot it. Like, for example, the word results and data here. You can plot like that. So, for example, information, which is shown here. For the word data is 6 times, and for the word result is 4 times. So you can plot here 6, 4. But this other one here, this is a data and result. This is 1, 1. So you can plot them like that, and you can see how it works. So this is the second method. So remember the first one was terms and documents. Now you've come to the second one, which is terms and terms, or words and words. But for words and words, remember you're using a co-occurrence. I mean, it's just a frequency count. How many times things are occurring together? So as I told you, I'm not going to get into details. You're going to read this. But then they're saying now, from these 2 vectors that we have, that is word to word, word to document and word to word, how do you extract now the information? There are several methods. One of them is called the pointwise to information, PMI. Some of these are in maths, so if you did some mathematics properly, you should have come across these. Pointwise mutual information, PMI. And the formula is here. Pointwise mutual information measure brought up by Church. So it's just some probabilities here. And at the end of the day, you might not want to be involved with the first principle derivation. But I think 19.4, formula 19.4 would give you the results. PMI would be, what is the probability of a word given context, which would be log to base 2 of the probability of a word given that context divided by the probability of the word alone multiplied by the probability of the context. I hope you got that story. It's just conditional probability. So if you want to know what's the probability of a given word, having seen this word, having seen the context. So it is simply log to base 2 of what? Of the conditional probability, that is the probability of the word given the context divided by the probability of the word multiplied by the probability of the context. So it's a simple formula. Those who did maths, you remember it. Then this has been improved by some other guys. They call it positive PMI. Just trying to improve it a little bit. PPMI. And they have now tried to use to maximize. So they're trying to maximize the probability of that given the context. You compare it between whatever you've computed with the PMI with the 0. So whichever is greater. Whichever is greater, we call it. So you only want things that are positive or 0 itself. So PPMI. All right. And here they have actually used an actual example. They are counting the PPMI of the word information and the word data. So the one that we had earlier on, information and data. And they are showing you how to calculate it. So who can remember what was the probability of these things? No, I can't remember it. This is information and data. They're actually up here. There are these ones here, 1, 1, and 6, 4. 1, 1, and 6, 4. So they have calculated it there. And you can just follow it up. So I said we are not getting into the too much details, but please go through during your own free time. Just go through this example. It's a simple mathematical manipulation whereby they are getting the probability of the word information given that the context is data. And this is the probability of the word itself. And this is the probability of the word, the context word, which is data. So they calculate it. Yeah, so that is using PMI and PPMI. Now let's move on. Suppose you don't want to use those conditional probabilities of PMI and PPMI. What else can you use? Are we still together, by the way? Or am I moving too fast? Are you still together?
Yeah.
Yes.
Okay. Romano and Orero says yes. Good. So suppose you are not interested with extracting the information using PPMI or PMI, the one you just seen using conditional probabilities. The alternative to that is using something we call TF-IDF. TF-IDF. And this just means term frequency. So you're just counting the frequency of the term, and you're dividing it by the inverse of the document frequency. So you're going to show you how you're going to do that. I don't know if it's explained here. Yeah, it's explained down here. But there's even another document that I had given you. If this looks too much mathematical, but it should not be mathematical. There's another one I have here. It just in our notes, and you have it. This is the last one, understanding TF-IDF, a simple introduction. So I think this one here. It's the same thing, but maybe this explanation here is a little bit simpler, less mathematical. But this term frequency, inverse document frequency, as I have said, it just uses the count. So it's it is a statistical measure that would evaluate how relevant a word is to a document in a collection of documents. And this is done by multiplying two metrics. That is how many times a word appears in a document, how many times it appears in a document, and inverse document frequency of the word across all the set of the documents. Inverse document frequency of the words across a set of documents. Let me give you an example so that you can be able to understand this. Let's use the word a term like AI. AI is a term. So I have 10 documents. I have 10 books. Some are from geography, some are computer science, others are from history, and so on and so on. So these are the 10 books I'm talking about. They are from different subjects. So I go there. So the first metric I want to calculate is what? How many times the word AI appears in what? In a document. So you go to document number 1, you say it appeared 2 times, or let's say 5 times. You go into document 2, it appeared 0 times. You go into document 3, so you get a whole document count for the 10 documents. But then you also get another matrix here, which is the inverse document, the inverse document frequency of the word across the document. So you ask yourself, how many times did the word occur in all the books? So for example, the word AI, it occurred in only 3 of the 10 books. So you get the inverse of that, all right? So 3 out of 10. So 3 books out of the whole collection, which is 10. So you get 3 over 10, so you get the inverse of that, which is 10 over 3. So you multiply that, of course, with the frequency there. So let's see whether they have this calculation. Yeah, here it is. So a term frequency is, there are several ways of calculating this frequency, with the simplest being a raw count. So you just count the numbers of instances a word appears in a document. So you just count how many times did it appear. Then there are ways to adjust the frequency by length of a document or by the raw frequency of the most frequent word in the document. So in other words, you can have 3 ways of doing this. You can have just a raw frequency count, just an account. But then sometimes there are some adjustments that are done in different algorithms. And the first one is you can adjust this by the length of the document. So if the document is too long and another one is too short, maybe the first book was only 10 pages, the other one was 1,000 pages. Do you treat them the same? So they are saying here you can adjust by the length of that document. So you can use some, what do you call them? Ratios. Yes. Or by a raw frequency of the most frequent word in that document. Now, the next matrix we said is the inverse document frequency. And this means how common or rare a word is in the set. So the closer it is to 0, the more common a word is. Do you agree with that? And they're saying this metric can be calculated by taking the total number of documents, dividing it by the number of documents that contain a word, and calculating the logarithm. All right. Yeah. So in other words, is the inverse document frequency. So just count how many books did it appear in, and then remember to inverse it. Here they are only saying they are not inversing here, but what they're saying is you divide the total number of the documents. So this could have been like 10. You divide it by the number of documents where it appeared. So it could have been 3. So it's 10 over 3. But then you don't stop there. You take the logarithm of that. Of course, the logarithm will make sure that it is a small number. So here we are. This is the term frequency inverse T. We simply call it TF-IDF. And it will take in the T, the D, and the D. What term are you considering? And the specific documents you're using and the set of the whole document. And then you, of course, take the term frequency. The term frequency, the term and that specific document, you divide it by the inverse of the number of documents where it appeared, that term appeared. So once you do that, yeah, IDF, and then you just compute it like that. Now, once you're able now to compute it, you can now be able to use it. And one application of the term frequency IDF is information retrieval. We've already seen one information retrieval method, and that is using the sparse matrix we referred to earlier in terms of the document to word matrix. I remember we had that. We had the Shakespeare, the Battle, and so on. But now this one can be more, and this is more common by the way. This IDF is more used in information retrieval. So TF-IDF was invented for document search and can be used to deliver results that are most relevant to what you are searching for. Imagine you have a search engine and somebody looks for LeBron. What is a LeBron? LeBron could be a book. The results will be displayed in order of relevance. That's to say, the most relevant sports article will be ranked higher. Because TF-IDF gives the word LeBron a higher score. LeBron must be something to do with the sports. Whatever that means, I don't know. But they're just saying that, the document will be retrieved is the one that, why don't we search and see? What is the rest of LeBron? LeBron.
It's a basketball player.
Is that what?
A basketball player.
Oh, it's a basketball game.
Player.
Oh, player. Oh, I think I'm behind news. I didn't know LeBron is a basketball player. Sorry for that. But yeah, this young guy here called LeBron must be a very good sports guy to be given in examples. But they're saying that, of course, he would only be found in sports books. So you'll not find him in computer science books, in history books, but you'll find him in computer science books. So they're saying you'd get him in sports books. Very good for that example. And that is the information retrieval. But last week, we also saw that there's this thing of a keyword extraction. keyword extraction. And we saw this is very important, like when you are dealing with the analysis of text. Like, for example, last week you gave the example of you are trying to do analytics on data that has been given by, let's say, for a certain product. Let's say Safaricom. Or even, let's say, even Amazon product. Amazon, they have a cloud, the AWS. So those Amazon guys want to see how their product is behaving in the market. So all they want to do is to go and because that would be too expensive to have billions of people who report, who comment on this AWS thing. It will be manually impossible to hire guys to, to be able to look one by one. So you use machine learning methods to be able to do automatic clustering of this information. So the easiest way is to look for keywords. So you can do a classification if you have some predefined words already. So maybe like delayed service or maybe service outage and all that. So you can run it through a classification. You see how many guys are talking about outages and so on. But if you have no idea of the keywords, then how do you go about it? You use simple clustering. So clustering will give you so many clusters of different, with different themes. And so you can look for the labels to give to these clusters later on. So those are the two key methods of applying this TF-IDF, information retrieval and keyword extraction. But they are all used in data, in text analytics. So the guy has some fine words here. Yeah. Let's go back to our book. Our book, we were on the alternatives for this PPMI. And so we are on this TF-IDF. And they have some formulas here for that. I think the formula is there here. All right, enough of that. Now, another way of analyzing this, of course, you've seen the first method is using the PPMI and its variant, which is the first one was PMI and its variant PPMI. The second one was using term frequency, inverse document frequency method. Now, the third method, I hope you're getting all of this, is now the so-called the similarity measure using the cosine distance. Now, this is the Euler distance. We covered it last semester or when I last taught you. And this is a cosine angle. Because you're dealing with the vectors, you can always get the cosine angle of two vectors. And if you remember your maths, this is simply the dot product of the two vectors, like showing this formula here. The distance between the vector v and the vector w is actually the dot product. It's actually the dot product. I hope there's an example here which you can work on. Yeah, there is a small example here. With apricot, yeah, it's here. So here is the formula, the dot product AB, which is the modulus of A or the length of A and the B and the cosine theta, which they've expanded here. Okay. And then they have tried to show you how because here it might look complex for those of you who don't like maths. They have broken it down, but these are just the summations. These are the summations. They have taken you back to the example of the apricot, the digital and the information, and these things. Yeah. So you have 201 for large, 016 like that. Or 200. If you want it, you can read it the other way around. For apricot, you have 200. Digital, you have 012, and information, you have 161. So you can apply. You can plug in these numbers into the formulas. Oh, sorry, I've skipped. Yeah, it's not fitting in on one page. Now it is. So you can see the numbers. So the cosine distance between sorry, between apricot and information would be that one shown there, which would be 0.16. So apricot and information. You can see in the table up there 200 and 161. All right. But then the second one is the distance between digital and information. Of course, we have 012 and 161. So you just plug them inside there. And then the distance would be 0.58. So you can clearly see that this is giving you some information that the distance between apricot and information is actually 0.16, whereas the distance between digital and our information is 0.58. So if you are to select which two words are similar or are close to each other, apricot and versus information and digital versus information, you can see now from this calculation, digital and information are close because they are 0.58. You take the bigger one. And that's how you extract the information using this third method of cosine angle. Is it clear how you're doing it? If it's not clear, then you can, of course, here you can go back to the notes and read slowly. But here there is the plotting, which you had done earlier. And you can see the words are tending towards one direction. Information, digital and information. You can see the one for digital is here, the one for information is here. So they're heading in this direction. Whereas apricot is actually facing the other way around. All right. Now, you can, of course, be able to see that using the cosine angle, we can be able to tell, to do some sort of clustering. And there's some guys who have done this, and they have been able to visualize this. There's a guy known as Rod. He did visualization. And you can see here there are some clear clusters. Like, for example, the word China, Russia, Africa, Asia, Europe, all these are in one cluster. But again, China and Russia are in a subcluster of their own. Somehow Africa and Asia are in another subcluster. I don't know why. Maybe they are developing countries. And Europe also is there. Then the Americas and all this, but they are all in one cluster. Then the next cluster here would be this one you can see. Let me make it big. Bull. No, this is not Bull. This is Chicago, Atlanta, Montreal, Nashville, Tokyo. So you can see these are towns. The other cluster is up here, which is quite big with 3 or so subclusters. Wrist, ankle, shoulder. These are body parts. Another one here is dog, cat, puppy, kitten. So you can see clearly with this visualization, you can be able to see the clusters even visually or manually. But of course, for a computer, you can visualize them or you can use the distances to do some decisions. Now, there are some other methods that I'm not going to get into too much because they are now in maths, but it's good to mention them. The other day I was telling you I went to France to work on some data on security. The guy I was working with is this guy here called Grafenstein. Grafenstedt has also come up with his own formula. So he was my colleague. We worked with him there. And they have what they call the Jaccard. The Jaccard is also a similarity measure. So the Jaccard similarity measure between two vectors v and w. They have shown their mathematical things there. The Jaccard. Yes. Now I think that would be enough of that. Now let's now move from the less dense vectors, the sparse vectors that we've talked about, and the way you extract information from them, either using the PPMI, the PMI, the cosine angle, the TF-IDF, and finally the Jaccard. Now let's try to make our vector more dense. Now we can make our vector more dense, and I had mentioned this area, by using two methods. The first one was the SVD. So it's a very popular method, dense vectors via SVD. There's a bit of mathematical treatment here, which I don't feel like getting into. But what they're telling you here simply is that these large vectors, they'll be typically 20,000 by 50,000. So I don't know what that size would be. 20,000 by 50,000. That would be 20 times 20,000 times 50,000, which is a lot of millions there, which is clearly sparse. Most of the numbers there will be zeros. So we want to get to more dense vectors, like a 50 by 50, smaller things. They're saying a sparse, no, a dense vector would be probably between 50 and even 1,000. 1,000 is also considered dense. Yeah, but most of the ones I've dealt with is between 50 and 100. So there's a method called singular value decomposition, or SVD. And in the next section, we introduce the commonly used neuropredictive SIBO and skipgram. So these are the two approaches: the mathematical SVD, or the neural network SIBO and skipgrams. Now, for you to understand SVD, there are some guys who have tried to apply this to. There's a paper that was published in 1988, and it's called the latent semantics indexing, or the latent semantic analysis. So that was the very first method of using these SVDs. But the point behind these SVDs is a part of, you can see there, SVD is a part of a family of methods that can approximate an n-dimensional data set using fewer dimensions. So including what we call the principal components analysis and the factor analysis and so on. So like using JPEGs and MPEGs, they use this PCA. So it's just a way of reducing from big to more dense vector. So in general, dimensionality reduction methods first rotate the axis of the original data set into a new space. And the new space is chosen so that the highest order dimension captures the most variance in the original data set. And the next dimension captures the most variance, and so on and so on. So it's like a continuous method of rotating vectors. So you rotate a vector, and then you get the deviations. And of course, where there's much deviations means that we have more information. Yeah. So here they have explained how they are rotating. We're not getting to that. And so on. But here is another example. of SVD applied to co-occurrence matrix X. So they have this example here. All right. So we have X, which will be broken down into. So let's see. Usually it is broken down into 3 vectors. So this one is being broken down into the word, and the last one here is the context, and the middle one is called the, I've forgotten the name, but it's like the rotating vector. So we call it the M, the small m. So you have the W, the M, and the C vectors. Yeah, so I'm just looking at the high level part of it. So in the SVD, you have this word. So you start with the matrix itself, and this could be a word by word matrix. Word to word matrix, which of course you could have used it for. You can use PPMI to do that. Now this word to word matrix would be, let's say, called X. Then you break it down into the 3 vectors I've told you: the W, the S, and the C. And now they do what they call the truncations, and then finally you get the embeddings. Is a WK. So the resulting WK is the vector you're interested in. So for now, I've just maybe have a bird's eye view of this SVD. If you're interested, I think there's a document. I don't know whether I included it in our notes. Let me just check whether. Maybe I did not. But SVD, you can even Google it anyway. Okay, I did not include that document. Usually I do include it. But you can even Google it from a mathematics perspective so that you can understand things slowly. SVD. SVD vectors. SVD dimension reduction, maybe. Dimension reduction here. So we can just pick even the first one that appears here. There are many texts here that are explaining this. I don't know which is the best. So I'll just open the first one that appears first of all. It may not be the best, but let's just open it. So here they are explaining. Oh, what is this now? Yeah, so they're explaining. They're explaining the dimensional reduction technique. Oh, yeah, it's good. They have explained the PCA, the principal component analysis, the LCA, and also the SVD. I hope he has done a good job. Let's see what he has done. He has explained this business of dimensional reduction. So he's explained the PCA, motivation for PCA, how PCA works. Pros and the cons. Yeah, let me send you this. This looks interesting. Please read it after, because of course with the little time we have, we may not be able to. So just click on that link I've sent you. I'll be opening. Yeah, it's actually opening. So just have a look at it and then later, not now. Huh? So just save it. Has it opened from your end? I've sent it on the chat.
Yes.
It has opened.
Yeah, very good. So I think that one will explain the three methods of a dimension reduction. Because we are dealing with the computer science. And you need to understand the science behind these, moving from these large vectors, which has many zeros, into the dense vectors. But as I'd say, this is work of maths, so we have to link it with maths. Let me just save it. So this way. LCA SVD. Good. All right. So now, once you've understood that there are those mathematical methods, so even if you read books, you'll be able to appreciate when you see these methods that they are simply techniques for the reduction. Yeah. So, yeah. Let me go back here to where we were. Or maybe you can take a moment and appreciate that document. Just take one moment and appreciate the document that you just downloaded there. Yeah, then I come back 1 minute only. Okay, so I'm back. So let's go on. You'll appreciate the document later. And now that we are done with those three methods of dimension reduction, there are some other popular methods that have been developed over the years, not so long ago, maybe over the last 8 or so years. And there are two popular algorithms, one called the skipgram and the SIBO. They're also available for download so that you can just download the algorithms or the code, and you can just embed it in your work. We shall just also do an appreciation of what it is. These two methods. So they say here that that a second method for generating dense embeddings, this now apart from the SVDs, draws its inspiration from neural network models used for language modeling. And recall from chapter 5 that neural network language models are given a word and they predict the context of that word. So really our goal here is you want to be given a word and you predict the context of the word. Alternatively, you can be given the context of a word and then you predict back the word itself. So this prediction process, it can be used to learn embeddings for each target word. And the intuition is that words with similar meanings often occur near each other in texts. So the neural models therefore learn an embedding by starting with a random vector and then interactively make a word embeddings more like the embeddings of neighboring words and less like the embeddings of words that don't occur like it. So just like in many machine learning, what they're saying here is that since you might not know what's the original vector of a word, let's say you've defined a 50 by 50 matrix, but initially you don't know what is the weights of these words, okay? So what you do is that you initialize by random values. The matrix is usually initialized with random values of those vectors. So as the neural network learns, the vectors will be adjusted accordingly, and the words that have similar contexts will tend towards the same weight. Okay, the words with the same context or the same sort of meaning will tend towards the same corner of the weights. So in other words, the weights will indicate similarity of words. So here they say that although the metaphor for this architecture comes from word prediction, referred to as word, after the software package that implements two methods for generating dense embeddings, skipgram and SIBO. SIBO stands for continuous bag of words. Like the neural language models, the word-to-vec models learn embeddings by training a network to predict neighboring words. But in this case, the prediction task is not the main goal. Words that are semantically similar often occur near each other in the context. So I think I've explained that already. And again, within the short time, I cannot be able to explain everything, but let's go to one of the two algorithms. And let's see what the context of this graph. So here they say that figure 19.8, which figure is this? No, this is 19.7. I'm trying to look for a nice place to start. So they say that the skipgram model, so I'm reading here. Or maybe let's read slowly. There's no harm. Let's just go back. There's no harm in reading slowly. I may skip too much and then you not understand anything. So they say that we'll begin with a skipgram. So that's the first algorithm. So like the SVD model in the previous section, the skipgram model will actually learns two separate embeddings for each word, W. So the word is the one that's W. So it will actually learn two separate embeddings. So the word embedding V and the context embedding C. I think that's a very important statement. I don't know why I had left it out. That for skipgram model, what you're actually doing is that for given each word W, which we are calling W, we shall learn two embeddings or two vectors That is a vector V and a vector C. So V is for the word itself, and C is for the context. Now, these embeddings are encoded into matrices, and the word matrix W and the context matrix C. All right. So I have the W and the C. So each row I of the word matrix W is the one by D vector embedding VI for word I in the vocabulary. So I think you noted that, that each row I, so you have the rows of the word matrix W. So within the word matrix W, we have the rows. And each of those rows, of course, if you just pick one row, it will be a 1 by D, which D is the length of that, that vector. So 1 by D vector embedding VI for the word I in the vocabulary. So in other words, for that particular word, it will be represented by each of the vectors. And they say here that each column I, now we are on the columns, of the context matrix, now we are on the different matrix C. So each column I of the context matrix C, now that will be the D by 1 vector embedding C for word I in the vocabulary. In other words, if you go to the context matrix, which we are calling C, and you take one of the columns, those vertical columns, that one would be actually the context of the word D that we are referring to, or of the word that we are referring to. So of course the word is the word I, because the I is an index which keeps on shifting. 1, 2, 3, 4, 5. So that's the interpretation of those two matrices. So here we are. We have the W, we have the C. So in the W, we considered the rows, and in the context, we are considering the columns. That's what we've just done there. All right. So the size here would be V by D, and this would be V by C. Oh, I mean VC by D. All right. Now, what we do is that this is your neural network here. Let me just, yeah. So this is your neural network with the first layer as the input layer. Now, what are you inputting here? This is called the one hot input vector. So here, we are inputting the vectors, which is the vectors of the words themselves. All right. So the vectors of the words. So for example, you have x1, x2, x3, all the way up to xv. So you'll have the various vectors representing that word. So input it. What are you predicting at the end? Have a look at what you're having at the end. The output layer. So this will give out the probabilities of the context words. So it will tell you that for the word that you gave me there, I have, for example, two context words, one on the right. You can see this is T minus 1. So there's the word on the left. And this is a T plus 1. So this is the context word on the right. So it will give you the probabilities of those context words. So I hope you are clear on this diagram. Let me repeat it. This is a neural network. What are you feeding it? You are feeding it the embeddings of the words. the embeddings of the words. And remember, these embeddings could be the long vector matrix that we discussed earlier on. So once you feed it for a particular word, one word, you will have now to get on the extreme right the probabilities of the context words. Let's say the word you have put here as your input, the word ugali. Let's say you have never heard of the word ugali. You've never heard of the word ugali. So that's your input. So within your embeddings, the ones we are calculating as the sparse vectors, you've already designed what is your vector for that word ugali. So you input it here. Now on the other end, you'll get what? The probabilities of the context words of the ugali. So you could have defined, I want one word on the left. This could be the co-occurrence. So one word on the left and one word on the right of that word ugali. So you might find things like eat ugali. It could have occurred a lot. So you'll pick the context of the word eat and get the probability of that word. What else would go with ugali? I'm looking for the context of the word ugali. When you hear ugali, what comes into your mind as the context words? Eat is one of them. What is the other one? Yes, are we still together?
Yes.
Yes. Which
Yes.
word was that?
There is mayai.
Yeah. Mayai. Yeah, he likes ugali mayai. So the other word would be mayai for him. which would be, of course, there are many context words, and you can define as big window as you can. So there could be mayai, another could be sukuma wiki, another one would be cook, ugali. So you can define the window. Of course, the bigger the window, the better. you can predict better, but of course, the more complex the model becomes. So you try to do an experimentation to see what's the best context window. So once now you can predict this, the output words, even the word ugali, you can now be able to determine where it is. And the beauty of this would be with the probability of the word ugali, I mean, based on the output, the probabilities of, I mean, the vectors of the output words, you might find the same context words are also occurring for rice and maybe chapati. So you'll be able to cluster ugali, chapati, rice all together in one area. So that's the principle behind these Mikolov's skip gram. So all you need to do is to know what's the input vector. And remember, the input vectors are, we have defined them somewhere here. So here, yeah, so the other one, sorry, let me just skip to that. The other one, okay, here Mikolov has tried, they have tried to explain how the vector for ugali would look like. So this is the one hot vector with dimensions corresponding to word wi. So it will be having so many zeros, of course, as you can see here. But this is the one hot vector. It's called one hot vector because everything is a zero apart from where that word ugali occurs. So a one hot vector is just a vector that has one element equal to 1 and all other elements are set to 0. Thus, in a one hot representation for the word, that one, so everything has a 0 apart from maybe just that one word, right? Then they say here, we then predict the probability of each of the two 2C, which two context words, output words. That means two output words, WT1 and WT plus 1. And the steps are here. Select the embeddings from W, that is from the word matrix. X is multiplied by W, the input matrix, to give the hidden or projected projection layer. So here they're explaining the workings of the hidden layer, which I've skipped in my explanations. The hidden layer, they're explaining how is working. But they're explaining it down here, the hidden layer. That under the hidden layer, what you're multiplying by what? Yeah. And then they compute the dot product. So they're using the dot product here. And then they normalize and all that. So you don't have to go through these details of this, unless, of course, you're interested with this. But the idea is that you can now be able to download a skipgram model, and you can be able to create your own dense vectors. Now, on the other side, we have the SIBO. I hope it's the one that's next. And the SIBO, is now the opposite of this. Let me show you what it is. This is a SIBO. So SIBO is roughly the mirror image of the skipgram. It is based on predictive model, but this time predicting the current word W1 or WT from the context. So in other words, you are given the context, you predict another word. Okay, that's what we are trying. You're given, so it's the opposite of the skipgram. So you're given the context, please give us the word. So you can see here now, you're given the context. So you're given the context of W. The context was T1 and T plus 1. So again, the window here is on it too. You take it through a hidden layer, and then you're able to predict the probability of the word. So you can either use SIBO or skipgram depending on your usage. And now this is now what we call methods that I've shown you. The skipgram and the SIBO, they are part of neural network application within these text analytics. They also call it deep learning. It's also part of deep learning within this context of within this context of text analytics. So again, you can get into the details here, which I'm trying to avoid because it will take us quite a number of lessons to learn all of them. But in a nutshell, I have been able to summarize for you very quickly all the vectorization methods that we have in this world. Now, if you go back to our notes, now that we know the vectorizations and how they are working, we just wanted to conclude this. Vector semantics. Let me open it again. So you have gone through the main document. There are several topics. There are several applications you can have for this. And one of them would be, for example, topic analysis or any other. So let's open the one for text analysis. Topic analysis. Topic analysis is under Monkey-Learn also. So it's one of the methods that it's one of the ways in which you can use all these vectorizations that we've said. Let me just make sure it's the one. Yes, so it's a good one. So where do you think you can apply topic topic detection methods? Topic detection, as I told you last time, you can use it for analyzing texts that people have sent, and then you want to see what they are talking about generally as topics. So I would like you to go and read this in details, but I'll just pass through it. So what is topic analysis? Scope of topic analysis, when to use it, why is it important? Then we go to the modeling itself, which is what I was interested in. Topic analysis is also called topic detection, topic modeling, topic extraction. So it's a machine learning technique that organizes and understands large collections of text data by assigning tags. So I think that's a very important thing that you like in your life as a text analytics expert. You want to get huge amounts of data and you want to assign a tag to a certain document. And so these documents are talking about this. Or remember, a document can also be a paragraph. So you can divide it into paragraphs and then say this paragraph is talking about this and so on and so on. So topic analysis is used in NLP to break down human language so that you can find patterns and unlock semantic structures within text to extract insights that help make data-driven decisions. And the two most common approaches for topic analysis with the machine learning are NLP topic modeling and NLP topic classification. Now, topic modeling is basically an unsupervised machine learning. So it's like a clustering. That's what they call topic modeling. Let me here. So topic modeling is what is machine learning technique. And this means it can infer patterns and clusters similar to expressions and similar expressions without needing to define topic tags or train data beforehand. Let me ask you a question. In Kenya, if I use the context, like if you steal, utakula maharagwe. If you steal, utakula maharagwe. What does that kukula maharagwe mean?
Which means going to jail and eating the beans there.
Yeah, going to jail. Yeah, for those who didn't know, kukula maharagwe means going to jail. But you see, if I used another context, like if you steal, you're going to go to jail. If you steal, utakula maharagwe. So all that, I can correlate the words. Even if I did not know what's maharagwe, I can tell that they have the same topics. So they can be clustered under the same kind of meaning. So you can infer patterns or cluster similar words. Utakula maharagwe, you'll go to jail, you'll do all this, and so on. Ama nitakuweka ndani. So all those means the same. So you can use this topic modeling, which is a clustering method, to help you do all that, or even classification. So in classification, you just have the keyword as you go to jail, then it will give you all the probabilities, all have similar probabilities. So in this document, they have explained how you can do that. But before that, text classification or topic extraction means that you have to know topics beforehand before you do the extraction. Now, topic analysis can be applied at different levels of scope. For example, for document retrieval, at document level. So the topic model obtains the different topics from within a complete text. For example, emails and so on. So remember when I started telling you when I was in France, the kind of work I was involved in, we could be able to tell people who are able to plan evil, even without using the normal English, or I think we're also using Spanish and other Arabic things. You can also be able to apply it at the sentence level and at the phrase level. So when is it used? When you have large, huge text amount of data. And again, you can use a tool like Monkeylearn to be able to do this topic analysis very easily. So you don't have to get worried about tools so much. So you can find out what people are saying about your product. And another one thing you can do is you can also do what you call sentiment analysis, which means that you can be able to tell whether sentiments are negative, positive, or neutral. So of course, with this sentiments analysis and also now topic discovery or topic modeling, you can be able to tell exactly what people are talking about. Besides branding or brand monitoring, there are many other uses for topic analysis, like the social media monitoring. I have supervised a guy, but this was a PhD guy, for this social media monitoring. We were doing what we call hate speech monitoring. So you can do hate speech monitoring. If you want, you can Google that from the internet. You can Google that and you find our work with that guy. So you can, for example, Google. You can Google. There's a guy called. There's myself, Mushemi, and Ombui. Hate speech modeling or hate speech detection, or just hate speech. Let's see what it brings out. So the first one, we have published several papers, but this is one of them. You'll see how we've used this topic modeling and so on and so on. You can download this. I think this is free. Psychosocial features for identifying hate speech in social media. Yeah, so this one typical. So this is we are using psychosocial features for identifying hate speech in social media text. This is actually text mining. So I'm sending you there so to go and read. I don't have to. Let me just give you a shortcut. But you can. There are many papers. I've just picked on one. Let me send it so that you can Google later. Has it come? Yes, it has come. But that's just one example I've given you of a book, of a chapter you published with a colleague. It was my PhD student. Now, the other one is, okay, sorry, I was just showing you here the kind of work. So, social media monitoring. You can have customer service. Customer service. We can have voice of customer analysis. So this is now over voice and so on. And you can do it at a large scale. You can do it on real time, and it has consistent data. So I think what I'll ask you to do, how does topic analysis work? So I think you read this document because of time. Topic modeling versus topic classification. You can go through this document, and then later on I'll give you, because I don't think we have a question on this. I'll give you a question on this text mining, and then we can be able to finish up the syllabus. So I could even pick one of these use cases that these guys are having here, so that I'll make your life a bit easy. Yeah, so you can see they are very interesting examples. I'm just skipping through. Like this is on brand monitoring and how they are doing it. How you scrape the data from, you scrape the data and how you organize it, and then how you put it on the Monkeyland. So please go read that document. I'll be able to formulate a question which you can do practically on this. Once we are done with, I hope the other one on data analytics is going on well. Of course, we will be finishing by 7th, you know that. I hope there will be no one wanting extensions. After that, we'll only have this text analytics, and then we are done with the syllabus. As you can see, even on the theory, I think I'm almost done. Maybe one more lesson on theory. Let me see what is remaining on theory. On theory, I have very little remaining, because basically now you've done vector semantics, you've understood its applications, and so on. But there's something I've skipped here. Text pre-processing. Please open it. Yeah, please open it. Again, because we've done pre-processing for data. Now, my machine is playing up on me. I'm opening too many things, doesn't like that. All right, there's the text pre-processing bit. Please go ahead and look at it. So any question from today's work? Am I audible? Because I think my machine is me a lot here now. Yeah, I think I'm audible. Am I?
Yes.
All right. Also, I was asking if there's any question. If there's none, then we can call it a day. Until no, tomorrow. Tomorrow, of course, we'll have our labs. Tomorrow we have our labs. I hope people will be able to finalize their works tomorrow. And then yeah, so things can work like that. So then I think we can stop there, and then we can meet tomorrow, and then we can finish this syllabus next week. Apart from the practicals on the text processing, we can finish it by next week. Thank you very much. Make sure you're filling the register. All right, so cheers.